Well, so far it's been interesting. I think that I'm on track because all of the speakers have spoke a little bit about what I'm going to talk about too, and I think the key word is, in this day and time, is efficiency. And so I'm going to talk a little bit about power devices, probably a little bit more on the technical side, and I'm going to have to go fast because I have more material than I can cover, so some of it, I won't read all of the words, I'll just talk to each slide. So if you look at power devices nowadays, what's a little bit different than I think than in the past is that I grew up in the background of device physics, but I think anymore, and we used to spend all the time on silicon, but nowadays the interconnect between the silicon and the package itself, I think there's like a 30%, 30%, 30% importance on all of this. So in order to understand how you're going to define a process technology or how you're going to define a device, you'll need to also understand everything about how you're going to package it and how it's going to be used in a system. So engineers have to be more and more complete in their thought processes today. So I'm going to speak a lot about specifically power devices, and I'm trying to operate two things at once, so I'm not very good at that. So. In recent years, the architecture of LDMOS devices, and I'm going to talk about integrated processes mainly, really haven't changed a whole lot, starting to slow down a little bit. And new things like super junctions, the figure of merit has changed about 20% each generation every 2 to 3 years. But I think it's reaching some limitations also. And today there are many competitors who have good figure of merits. So differentiation is, I think, is really more in characterization, robustness, and reliability. So improved safe operating area, channel hot carrier, and power metal with bonding over active area. So we've also done some things to make the technologies better, like create high voltage nodes and low voltage nodes so that this allows more density and optimization without the sacrifice of high voltage spacing rules. And then modularity was a word used probably 15 years ago. It's back again because people want simplified low-cost flows. And then I think in power devices, new figures of merits like resistance times charge is important because the manufacturers of the end products out there are wanting to switch power supplies at much higher speeds now, and probably 5 megahertz, and there's also talk of 20 megahertz, et cetera. So this is a challenge for the power devices in these designs. So in the packaging area, world-class performance, QFN, WCSP, and multi-chip modules are becoming more of a normal type package. And copper wire has a higher performance, lower resistance, and is much, much lower cost than gold wire, of course. So I think that we can't count out discrete technology. It's a big piece of the chart, and we have to continue to look at it in our solutions. If you look at the power device TAM, which I think this is about correct, maybe 20 to 22 billion, and on a kind of industry standard growth rate other than the first of this year. What you see is power ICs, so this is the integrated type circuits, about $8 billion. Low voltage discretes below 40 volts, about 4 billion, and other discretes about 8 billion. So other includes everything that's higher than 40 volts all the way up to 3 kV. So this includes things like silicon carbide, gallium nitride type devices also. So I don't know if they told you, but you have to take a test before you can leave. So how many people in here know what these numbers are? Or how about these numbers? Or how about these numbers? Well, actually, Gabriel talked about some of them. So these are like battery levels, which are based on chemistry, and industrial standard supply voltages, and not only just supply voltages, but other determining things like the white LED is a big determining factor in a lot of circuits nowadays, and then strings of LEDs, and then things like standards like automotive load dump, and then telecom and safety and different things. And then there's CMOS levels, because the CMOS generation of processes have always led in the process technology world, and the analog technologies tend to follow. So these actually dictate, I'm going to say BCD technology, power devices. So if you were a device designer for power, these are your care abouts. This is your customer. You have to understand how the engineers and how the systems use all of these things to be able to generate the right voltage levels and the technology to meet these requirements. And on the high voltage end, you have things like, again, telecom and maybe solar microconverters for panels in the 110 type volt range. And then you have medical type applications and more solar applications in the 200, 300, on and offline AC, and also, you know, LED lighting in this type of areas generate quite the necessity for quite high voltages because of the AC mode of them and transients, etc. And then you have the very high voltage area where they're building modules that are actually running the motors on trains and boats and all kinds of stuff like that, and also solid state energy conversion. So I'll talk a little bit about resistance and voltage. Probably the old and most talked about figure of merit is a specific on resistance versus the breakdown voltage, BVDSS. And of course it's important because it relates to the device size and competitiveness. And silicon area versus process complexity and cost, you know, is a big key item. So if you look at this chart, it shows specific on resistance here versus breakdown voltage here. And basically, the specific on resistance goes at about a 2.5 power of breakdown voltage. What that means is if you increase the breakdown just a little bit, of course the on resistance goes up significantly. Also, you'll notice there's a trend that you move away from this theoretical limit here for silicon as you get smaller. And that's because in the lower voltage devices, a lot of the area is what I call inactive area, and you can't get away from not having contacts and stuff like that. So it's more difficult to get close to this line unless maybe you go to 2 dimensions or 3 dimensions. So here's just another picture of the low voltage range, because the low voltage range, say 30 volts and below, is very important. It's probably somewhere around 70% or of the total market in power ICs. So I wanted to mention, when you look at that chart, the way they operate that number is they take the IDS curve and they look at the resistance load line for VGS max, and the inverse of this slope, which is V over I, at about 0.1 volts is the resistance that they measure for one of these power devices. And then BVDSS sometimes is much greater than the rated maximum breakdown voltage of the device. And so this is what determines the RSP type figure. So the closer you get this to the actual absolute max, then the lower your specific on resistance and the smaller your device will be. So if you look at a typical LDMOS device, what I was talking about before is you have what I call active area. So you have a channel and a source and a drain region over here, and current flows from source to drain, drain to source, depending on how you want to look at conventional or reality. And then you have an inactive area where you have to have contacts. So the area part of this equation is made up from the length of the device and then these areas here. So with scaling and advanced lithography, you benefit a lot in this area here because it'll scale with the technology. But the voltage limited scaling in here doesn't scale much. So these devices, so low voltage devices, since this region here is small, benefit a lot from scaling lithography, and high voltage devices do not. So if you look at advancements in the LDMOS device types, this is kind of a generic looking, I'd say, older type LDMOS device. And this is a more modern, what we call drain isolated device. Here you have the source region and the body and all, which is a P region in a big area of N-type material. Here you have the drain region, which is N-type and a big body of P-type material. And then it's isolated by this buried layer and this N-type material over here. This is pretty important about efficiency because this type of device allows tying the guard ring to any potential you want to. So when you operate the device, depending on the application, you can both sync and source carriers from ground. So in a way, you don't use any energy in the minority charge loss. So it's kind of a trick. And then in the more modern technologies, which you could build any of these type of devices, moving more to the shallow trench isolation type of technology is probably a little bit where the state of the art in power devices is right now, at about the 0.18 to 0.13 micron node. So in power devices, you can have as good a RDS on times area as you want to, but if they're not robust and they don't meet the breakdown voltage, then they're not very good to use. So we have to do a lot of characterization on power devices. And some of this is pretty complex stuff. This is a maximum IV characteristic for maximum gate. And then there's what's called electrical safe operating area, which is determined by the avalanche multiplication breakdown of a parasitic NPN device. And there's thermal SOA, which is characterized by thermal generation of carriers that cause failure. This boundary is fixed by the device and the electrical properties, but this boundary can move. It could be inside of here, it could be outside of here. So packaging, interconnect, and things like that play a big role in the thermal boundary. And then also you have to look at things like a channel hot carrier degradation of parameters and guarantee that those parameters don't move over years. So this is just a chart showing when you talk about channel hot carriers, providing the engineers who are doing the design with a means of understanding how they can operate their device to make sure that it doesn't, that it's good for many years. So when you talk about this in terms of efficiency, you don't want your device to degrade in IDS on or RDS on or any of these parameters, otherwise it won't be working as efficient as it was initially. So long-term reliability is important. So the other thing that I would say is probably 15 years ago, you know, your device might have had a leakage current of 1 milliamp or something and nobody said anything. Today maybe your device needs to have a leakage current of 1 nanoamp or even less. So this is a real challenge. So the paying attention to what I call off state or quiescence. Quiescence means in rest. And so in that state is very important, and I think a couple of the speakers previously mentioned that because you need your battery to last a long time. So especially in mobile applications, the off state performance is very important. And this gets a little bit tricky because with the trend to have thinner oxides, lower voltage gate drives, smaller pitches, reverse leakage, you know, just like in the CMOS area, could start to be a limiting factor, and in order to get around that, we have to do some maybe design tricks or other things. Power metal. So in power devices and power ICs, metal resistance is hugely important because most of the integrated type circuits use lateral devices, so they have current flowing laterally in metal. I guess to kind of give you an idea, maybe building a device looks something like a bunch of stripes like this, and these might be stacked metals on top of source and drains. And then they'll come across with another bus like this, and then they'll put some, bond it out. And so my boss asked me one time, he said, "What's so difficult about a single transistor?" And I said, well, some of the transistors we're designing today have 3 meters of W in one transistor. So 3 million microns. I said, if you put that into perspective of, say, the 1 micron generation, so TI is kind of a DSP-oriented company, or was, I said, that's like 3 Pentiums. 3 Pentium processors that we're trying to switch every transistor off and on at the same time. So that gets to be a challenge with all of the metal and capacitance across the device. So another way maybe of doing it is changing up the busing structure so that you cut these lines into smaller and smaller segments. So when the device is on, you have current, say, flowing into this bus, and then it flows into this is the source side, into these source buses, flows across to these other stripes over here, and then down those stripes to the source stripes. And on the drain, you'll have just the opposite effect happening there. And so the current flowing laterally in this metal creates a big problem. And to show you a little bit how that works, current flowing in this device like that gives you a characteristic across the device that has a VDS that looks like this from one terminal to the other terminal. So this line, what you would like for it to be is straight or flat. And any of this curve, or we call it debiasing, the area in that curve there basically is inefficiency or loss due to the metal system layout. So we can do a lot of things with placement of bond pads, geometries, and things like that to remedy this and get that characteristic to looking more smooth. So this looks like a very simple type thing, but you can imagine if you were trying to build a transistor that's 10 or 5 milliohms, which, in case you're wondering, that's smaller than, say, most little bitty wires that you're working with in the lab or something, then it gets to be a challenge. You could have 20 or 30 bond wires on there. You could have 7 or 8 large blocks of these devices. And so the whole thing about this is the power metal system, or this system of metal, becomes really important to power devices. And that's a challenge because it's not good for density in the CMOS area and the other analog circuit area. So some of the areas of metal that they use in power is, of course, they'll have the integrated levels of metal, however many there are, and maybe they'll have a thick layer of aluminum, or either today we have plated copper with nickel palladium that looks like a lead frame on top of the chip, and so you can bond directly on top of that anywhere's on the chip. Or maybe we'll use some copper damascene from the advanced CMOS technology area because it has lower stress, has bondable metal capability, and it's isolated nicely by design since it's put in a trench. So what I call the operating states, specific on resistance and breakdown is still very important. And the device has to be robust in all of these states. Low voltage reverse leakage is extremely important, and smaller line widths limit the geometry layout, and also metal resistance issues with the small line widths and electromigration properties all limit the way that we can design the power device on the chip. So if you put more metal layers, that's not so good because it adds cost. So we do more with innovative geometry and layout methods. Okay. So I want to change a little bit to efficiency and switching losses. The trend in power to switch at higher frequencies. Right now, a lot of converters are maybe 200 kilohertz to 600 kHz, and some of them nowadays are 1 megahertz, 2 megahertz. But the trend is to move more towards 5 megahertz, 10 megahertz, and if you look at envelope tracking, which they want to do with supplies, is at 20 megahertz. This is actually really a challenge for large power devices. So, but the reason they want to do that is because the end guy out there who's building the system, it allows him to use much smaller external inductors and capacitors. So it's lower cost, smaller form factor, and energy savings in those devices out there. But for us creating the power devices, it creates a real big issue. If you look at a simple synchronous buck inverter, Gabriel talked a little bit about these. You have a FET up here that turns on and off and gets current going in this direction. And then you have a synchronous FET down here that they operate actually reverse when the current goes in this direction. So the reason this is better efficiency is they build this device here very large. Usually it's 2 times the size of this or 1/2 the resistance. By doing that, the IR drop in this is less than a diode drop if you used a diode in here. But of course it is more expensive because it's a big transistor. So the problem comes in, but if you look at the efficiency though, efficiency curve looks somewhat like this. So this is the load current here, and this is the efficiency here. And usually what you see is something about like this. And so at low load current conditions, usually you get a lot of fall off. So if you can switch at higher frequencies, at low load conditions, your switching losses are a bigger percentage of your overall losses. And at high load conditions, you're at high current. So I squared R is a much bigger loss out here. So if you think about what's happening, there's some time period and it's switching from on to off, and it just continues to do this in a converter. And there's a transition time down here. So to get the faster switching speeds, the transition time also has to get faster, because as you narrow T down, this transition times. Today, probably for say a 30 amp part, 20 volts, maybe they're switching at 6 to 10 nanoamps for this transition time here. They would like to get down to about 1 nanoamp. And of course, when you do that, the DI/dt rate gets very, very high. So that causes, and we're always got that inductor out there. So what happens is on the switch node or the output node, you start getting a lot of ringing. And this ringing in one way actually doesn't cause a lot of problems with the conversion. It actually is more efficient. But the perception of it is bad. And the other thing is if the overshoot is very high, then you have to have higher breakdown voltage of your device to compensate for the overshoot. That means higher specific on resistance, and then your device would grow. So all of those things are conflicting with where we want to go. But this is a serious challenge for going to higher frequency, and higher frequency we're going to have to go to. So the things that create this are all of the inductances in the system. You have bond wires, you have metal systems, and you have an inductor out there that is your inductor that you're converting through. And you also have a diode in there that you're switching back and forth from the on state to the off state, and it has a large reverse, what's called a reverse current, and a recovery time. And so these things reflect back through the Miller capacitance and turn the device off and on, and so you just continue to get this ringing state happening, and switching faster just is a bigger problem. So you can do a little bit with the silicon technology to reduce the stored charge and junction area capacitance and stuff like that to reduce the reverse recovery. But still, there's going to be a lot of challenges ahead to get the higher frequency, I think. So I think the reason I mention this is because high frequency we got to go to. And so the challenge for device designers is going to be working on some things that probably they haven't worked on in the past. Instead of RSP, they're going to be more thinking about the device and how to get lower charge. Okay, so that was just a little summary. So what's happening with packages? Well, they used to look like that, and then that, and then that, and then that, and then, so it's pretty simple. They're getting smaller in all dimensions, not only in area, but also in thickness. And packaging has become a hugely important thing for power because if you think about it, the chip size that they're doing, which I'll show an example in a minute, so just let me go through a couple of these. If you look at the wafer chip scale package, 25 pin example here, basically you can see that it's going down smaller and smaller. This is 1/4 the size of this one, so however small they can make the ball pitch determines the size of the chip. If you look at the QFN type of scenario, then thinner and thinner and thinner is the name of the game. So getting down to like 0.4 millimeters means that we have to keep continuing to thin the wafer thickness down also. So from the silicon point of view, it gets to be a challenge for power because thin wafers with a lot of metal on them and thick metal, there's a lot of stresses, there's a lot of thermal mismatch coefficients of expansion, etc. So there's a lot of stress on the wafers that has to be dealt with to be able to put them into these thinner and thinner packages. So to give you an example, here's a 6 amp buck. Funny, Gabriel might have worked on this when he was at TI. And then here's a newer version. So this one here on this side is in a 0.72 type process, micron process. And you can see 59 milliohms types of RDS on, 6 amps rated device, 20 volt type device. It's a synchronous buck converter. Has 2 power switches in here, a bunch of logic and stuff. And then going to a 0.35 micron node, the change is drastic. Still a 20 volt device, still 6 amps. This is to scale. So almost a 5.7x reduction in size. IQ shut down quiescent current from a magnitude smaller, switching speed, almost 3x. And then actually a little bit more efficiency and a little bit smaller RDS on. So it's quite amazing what we're doing with the power stuff out there. So the problem though is, going to 0.18 or 0.13 microns, I don't know. So I think the whole conversation on Moore's law for analog, it doesn't apply. It does for high mix signal things where you have a whole lot of digital content because obviously you want to get the digital smaller and smaller and smaller. But it has the opposite effect on things like power devices and analog things where you need more metal, wider buses, and stuff like this. So RSP I don't think is going to be changing, RSP I don't think will change as much in the future as it has been. The other big problem is this device, obviously the power density is much, much greater than this device. So it's the same current and it's the same voltage, but it's much, much smaller. So, but if you need a digital block, of course, you're going to need to go that route for smaller lithography. but IQ may be higher. So we have to make choices because the core CMOS on advanced technologies, the leakage gets greater. So a big thing that's going, multi-chip packages used to be a nasty word in the industry, I think, but nowadays it's a normal thing to do. So we do multi-chip packages every day. So one way to solve the problem is do your logic and all of that stuff on an advanced technology, do your power and analog on another technology that makes sense, and put them in a package like this one's got 3 things stacked together. This one has a couple of stacked dies in it and then another chip in it. So there's lots of ways to configure the devices. So the whole thing I'm just trying to say is that packaging technology today is extremely important for power ICs and maybe all ICs, and probably a differentiator for companies in the industry and their solution offerings. So just a little more here on the package. The big issue is as we get smaller and smaller and smaller, the power density is going up. And we used to say by the square, but now since we're getting thinner, it's really going up cubically because it's a volume type thing. So the electrical, again, the guys who are designing these things in the application still want 6 amps, they still want 20 volts. So the electrical power stays the same, but the power density is increasing by the square and the cube, which is a big deal. So what that means is that a lot of the development of power ICs is in thermal management. So there's a lot of work being done now in thermal modeling and all of these type of things, and how to get rid of the thermal energy out of the package. So if you look at this chart, I just wanted to mention a little bit about, basically this shows current and voltage over here. So, I think that solutions for monolithic type ICs in an integrated IC process are good up to about probably 20 amps, and that falls off a little bit as you go out to say 30 or 40 volts. And then from 30 to 40 volts, maybe it starts around 10 amps and falls off down to about 3 amps or something like that. So this is, and then if you go to high voltage technologies, say 100 volts up to 700 volts, then we're really probably talking about current levels below 3 amps in a monolithic solution. So that is why discrete devices are also so important in the industry and still such a big, actually a big market area, is because to get to the high power levels, meaning high current with voltage, you have to go to some kind of discrete devices plus some kind of integrated circuit to control the device. So just to summarize a little bit, integrated power devices need both great on and off state and switching efficiency. And a lower RSP may be reaching a limit that is decided by metal issues or off-state leakage performance. Will smaller lithography nodes have any benefit to reducing RSP? I don't know. Unless a large digital content drives density, or you go to a smaller package with the same performance, or the same package with added functionality. So all of these things can drive the technology or the decisions on what technology you use to design your part. So higher switching frequency brings a new set of problems. Can switching losses be managed with device engineering? Packaging continues to get smaller and thinner, so power density, thermal management is a big issue. Multi-chip modules are becoming a norm. Off-state leakage performance is still of great importance. But the big question is, and I think somebody else mentioned that in their slide, that is, how do other materials play a role in power devices for high speed and high power density? So silicon carbide is been around a long time, and now I think they're going to release 6-inch wafers or 150 millimeter wafers on it. So that's hugely important because silicon carbide is about 10 times the cost of silicon. So the thought process is, and they also have normally off type devices now for power that have great leakage and great performance. So the thought process is maybe that will reduce it down to 2 or 3 times the cost of silicon, which will be a very important deal. And then there's a lot of work in gallium nitride in the industry now. A lot of talk about there's been some devices released already, people talking about releasing more devices. I've done a lot of looking around, and the issues I see on gallium nitride is nobody will tell you what their leakage is. Nobody will tell you what their defect density is, and it is high. And every vendor of material has a different flavor of epi. But what is nice about gallium nitride is that it's a hemp design. It has very excellent performance. It doesn't have a diode, so you don't have reverse recovery. So you can switch very, very fast. So it might be a player in the multi-megahertz switching range, tens of megahertz and stuff like that. And the other thing is it looks interesting even at low voltage. But I think silicon carbide may be very good for the high voltage applications greater than, say, 700 volts. And that's a very important market, especially for high-powered LED lighting, solar conversion, and different things like that, and AC offline type stuff. So with that, I'd just like to thank the few of my fellow colleagues who I stole some of the slides from. And 감사합니다.